So the next thing we're going to do is look at how to take partial derivatives when the powers get a little bit more complicated. So we'll do two examples here and then we'll move on from there. We're going to start with the function g of xy is equal to 7x squared y cubed. Now this function has one term, but it's made up of three factors. The three factors are 7, x squared, and y cubed. So you can think of this as 7 times x squared times y cubed. So if we take the partial derivative with respect to x, then y behaves like a constant. And in particular here, y cubed behaves like a constant. So the first step that we want to do when we take a partial derivative here is isolate all of the factors that are constants together inside of a parentheses, and then the variable portion, in this case the x portion, goes outside, typically on the right. So that would look like this. We would take the 7, which is certainly a constant factor, and y cubed, which is a constant factor, and put them together. And then the variable portion, x, goes outside. And x is variable here, once again, because we're taking the partial with respect to x. So you can think of this as some constant, some number, times x squared. So think, for example, of like 5x squared. How would you take the derivative of 5x squared? Well, you would take the power of the 2, you would multiply it by the 5 in the front to get 10, and then you would reduce the power on the x by 1. And we're going to do exactly the same thing here. The rule doesn't change for powers in multivariable functions. So to take the derivative, we would simply take the 2, bring it out front, multiply by the constant that's already sitting there, 7y cubed, keep the variable x, but reduce its power by 1 from 2 down to 1, which we'll just write as x by itself. So these are all factors that are being multiplied by each other, so we can simplify this. 2 times 7y cubed times x is the same thing as 2 times 7, or 14, and then xy cubed, putting the variables in alphabetical order. So the partial derivative with respect to x here is the expression 14x y cubed. Now if we move to the partial with respect to y, we're just going to follow the same exact process. Now y is the variable and x behaves like a constant. So in the original function g, 7 is a constant and now x squared is a constant. So we rewrite g as a constant, 7x squared, multiplied by a variable piece, or a variable factor, y cubed. So this looks like some constant times y cubed. To take the derivative, we take that power 3, multiply it by the constant in front, and then reduce the power on the y by exactly 1, from 3 down to 2. And when we clean this up, 3 times 7 gives me 21. We have x squared and we have y squared. So those are the two partials of g. So here is an example that uses a joint cost function. C of xy is given here, and our task is to find the partial derivative with respect to x at the point 160, 120. Now, before we do the calculations, it's important to sort of stop and think about, well, what are we actually doing here? We're taking the partial derivative with respect to x. Remember, if you go back and look at the original statement of this problem, x was the number of items produced at a factory. We called that factory capital X. And little y was the number of items produced at another factory called capital Y. So the partial with respect to x is a measurement of how the total costs are changing if we allow the number of items produced at factory X to change, but we fix the number of items that are produced at factory Y. In particular, if we were to look at a marginal interpretation, we'd say if we've currently produced 160 items at factory X, and we produce one more, the 161st item, by how much does that increase our total costs? So that's what we're doing here when we compute this number. Keep that in mind. So let's talk about how we would actually compute this. We'll start by rewriting the function so that any mixed terms are in the proper format that we've just discussed. So you'll notice the mixed term 7xy, I've rewritten that as a constant 7y multiplied by the variable factor x. So I'm moving all of the constant factors inside the parentheses just like we've been doing with the previous examples. The next thing is to actually take the partial derivative of each of those four terms. The derivative of 2x squared is 4x. The derivative of 7yx is the derivative of a constant times x, so its derivative is the constant 7y. The derivative of 7y squared is 0 because y is behaving like a constant when I take the partial with respect to x. And of course the derivative of 800 is 0 because 800 is a constant. So my partial with respect to x is the expression 4x plus 7y. That is like a formula, and it tells me how the costs are changing when I allow x to vary, but I fix y. Now, at the point 160, 20, I plug in those numbers into x and y in the right places, and I get $1,480. So our interpretation for this number is that when 160 units have been produced at factory X and 120 units have been produced at factory Y, the total costs of production are increasing by $1,480 per additional unit produced at factory X. Remember, nothing's happening at factory Y. The other way to say this would be the 161st item produced at factory X increases the overall costs by $1,480. Now we move to the partial derivative with respect to y at the point 160, 120. So as before, we rewrite the original cost function so that the mixed term 7xy is in the proper form. So in this case, since we're taking the partial with respect to y, x is behaving like a constant. So 7 and x go together as the constant multiplier, and y is the variable and stays outside. So now we can start to take partial derivatives. Remember, we're taking the partial with respect to y, so x behaves like a constant. So 2x squared is also behaving like a constant, so the derivative of 2x squared is 0. The second term, which is mixed, looks like a constant multiplier times y. The derivative in that case is just the constant, so in this case it's 7x. The third term, 7y squared, has a derivative of 14y, because again, remember, we're taking the partial with respect to y, that's our variable, and 800 goes to 0 as before. So the partial derivative with respect to y is 7x plus 14y. When we evaluate this at the point 160, 120, we get 2,800. Our interpretation in this case is that when 160 units have been produced at factory X and 120 at factory Y, the total costs of production are increasing by $2,800 per additional unit produced at factory Y. Remember, we have to say per additional unit at Y because this is the partial derivative with respect to Y, and Y is being allowed to change. So again, we're back to rate of change in units. This is dollars per item produced. The other interpretation is to say that the 121st item produced at factory Y increases the total cost of production by $2,800.